Hi everyone. Today we're going to be talking about stoichiometry problems and how to use the ideal gas law when we are not at STP. So if we are not at standard temperature and pressure, we can't use that nice conversion factor, 22.4 liters in a mole. We instead have to do a little bit of extra work. So prior to us doing that, let's take a look at some choices we have when we are solving these kinds of problems. There's two sort of methods, two different ways that this could be done. It's all dependent on what you're starting with. So if you are starting with gas volume, what that means is you're going to do the ideal gas law first, which is PV equals nRT, and you're going to solve for moles of gas. Then you're going to go do stoichiometry using that moles of gas to calculate whatever you're being asked to do. But if you are being asked to find the gas volume, instead, you're going to start with the stoichiometry because you're going to be given grams of something else. So you're going to find moles of the gas, and then you're going to use PV equals nRT second. So if that seems a little bit confusing, we're going to be going over a couple practice problems with it. So let's say, that should be an arrow there. Let's say we are trying to solve this problem. So we want to determine the mass of KO2 needed to react with 2 liters of CO2 at 895 torr and 35 degrees Celsius. So because I'm given volume of the gas, what that means is that first I want to use PV equals nRT to find moles of CO2. Then I'm going to do stoichiometry to go from moles of CO2 and convert that into grams of KO2, which is what I'm being asked to find up here. So I'm going to break this down into these two steps and set them up below. So our first step is going to be the PV equals nRT. So let's identify our variables. We've got pressure at 895 torr. We've got a volume of 2.00 liters. We don't know the moles of that gas. We know that R is always 0.0821 and the temperature is 35 degrees Celsius. So I'm going to change my torr into atmospheres. 760 torr in 1 atmosphere. That becomes 1.1776 atmospheres. And then I'm also going to want to convert that Celsius into Kelvin. This is 308 Kelvin. So if I plug this into my equation, PV equals nRT, pressure is 1.1776, volume is 2.00, N is our unknown, R is 0.0821, Kelvin is 308 Kelvin. What I find when I go through and do the algebra for this is that N is going to be equal to 0.093 moles of CO2. So by doing this step first, I'm able to find the moles of CO2. Now I can do the stoichiometry, where I'm going from 0.093 moles of CO2. I want to use the mole ratio to go from moles of CO2 to moles of KO2. And if I look at my balanced chemical equation up top, it's 4 and 4. Moles will cross out. And then I want to go into moles of KO2. Grams of KO2. So I have to add up how heavy 1 mole of potassium oxide is. In this case, it's 71.09. So this step here is the molar mass. We've done this before plenty of times. This is stoichiometry. So we find that this mass is going to be equal to 6.61 grams of KO2. So to recap, I had to start with PV equals nRT so I could find moles of the CO2. Then I do stoichiometry to convert that to grams of KO2. Let's try another one here together. So this is not balanced, so I'm going to balance it for you so you have those coefficients, but let's read through. We're going to determine the mass of H2O2 needed to produce 275 milliliters of oxygen gas at 1.15 atmospheres and 27 degrees Celsius. So because I'm given volume of a gas, so that's volume of the gas, that means my first step is going to be PV equals nRT to find moles of oxygen gas. Then I'm going to go from moles of oxygen gas, convert that into grams of H2O2 using stoichiometry. So I want to do the PV equals nRT first. So let me get this stuff out of the way here. It's not what I wanted. I just wanted to erase that. Okay. So PVNRT, pressure is 1.15 atmospheres, volume is 275 mLs, N is unknown, R is 0.0821, and our temperature is 27 degrees Celsius. Before I can plug these in, I do need to convert this volume into liters, so this is equal to 0.275 liters. And I also need to convert my 27 degrees Celsius into Kelvin. This becomes 300 Kelvin. So now that that's done, I can plug this into my equation, no problem. 1.15 is our pressure. Our volume is 0.275. N is our unknown. 0.0821 is R, and T is 300. So going through and solving this algebraically, we're going to find that N is equal to 0.01284, and that's moles of O2. So now that that first step is done, we finished that already, we now want to convert this moles of O2 into grams of hydrogen peroxide. So I'm going to do that step second. So I know I have 0.01284 moles of O2. I want to go from moles of O2 into moles of H2O2. So if I look up at my balanced equation, it's 2 and 2, easy enough. And then I want to convert moles to grams. I can't fit that in there. And then grams of H2O2. Sorry, it got cut off. So that's molar mass is 34. If you add up the two hydrogens, the two oxygens, we find that this is equal to 0.87 grams of hydrogen peroxide. So I had to do the ideal gas law first to find moles of O2. Once I found moles of O2, I could then do stoichiometry to find grams of hydrogen peroxide. Last one we'll do together. This is another one where we have to balance it to start. So to balance this, we'd have a 2 here, 2 here, and a 3 here. And now in this case, we're being asked to determine the volume that can be produced by 0.725 grams of KClO3 at 726 millimeters of mercury and 26.5 degrees Celsius. So this one's a little bit different because now we're being asked to find the volume of oxygen. So we can't really start with PV equals nRT because we don't have volume and we don't have moles of oxygen. So that means first I'm going to do the stoichiometry to go from grams of KClO3 into moles of O2. Then I'm going to do PV equals nRT. Okay? So to do the stoichiometry to start isn't too bad. We're just going to take that 0.725 grams of KClO3. I want to go from grams to moles for that, so that's going to be its molar mass. So I add up the potassium, the chlorine, and the 3 oxygens, and that weighs altogether 122.5. So grams will cross out. I then want to use my mole ratio to go from moles of KClO3 to moles of oxygen, and that's a 3:2 ratio. So what I find is that I am going to use 0.0088746 moles of O2. Now that I've figured that out, I'm ready to solve and use PV and RT because now I know N is 0.0088746. My volume is unknown. That's what I'm trying to figure out. My pressure is 726 millimeters of mercury. R is always 0.0821. And our temperature is 26.5 degrees Celsius. So the only thing I have here to convert is going to be that millimeters of mercury. I want to turn that into atmospheres. So there are 760 millimeters of mercury in 1 atmosphere. This is equal to 0.955 atmospheres. I also need to change this temperature over this becomes 299.5 Kelvin. So now that that's done, I'm ready to go ahead, plug in these numbers. So PV equals nRT, pressure is 0.955, volume is unknown, N is 0.0088746, R is 0.0821, and T is 299.5. Sorry, that got cut off there. So if we solve all the stuff on the right side of the equation, we find that that is equal to 0.2182. Then I'm going to isolate V by dividing 0.955. This is equal to 0.228 liters. And that's our final answer. So to recap, if you're starting with the gas volume, first you do PV equals nRT, then you do Stoich. Okay? If you're finding the gas volume, first you do Stoich, then you do PV equals nRT. Okay? So hopefully that by this point you're now able to solve these problems when we're not at STP. So when we can't use that nice conversion factor, how do we work around it? And this is how you do it.